Last time we have studied a theorem about bounded above sequence, monotone sequences we are studying, and last time we have proved a theorem for a non-decreasing sequence. If Sn is non-decreasing sequence and it is bounded above, then it is convergent. Sn is convergent, that we have proved. And a corollary about this is the sequence 1 plus 1 by n to the power n is also convergent. So this result also we have proved. Now next result is that is theorem 5. A non-decreasing sequence which is not bounded above diverges to infinity. So this is our next result. Non-decreasing sequence, or in simple sense increasing sequence we may consider, which is not bounded above. It will diverge to infinity. So this we have to prove. Now we shall prove the result. Let Sn be a non-decreasing sequence which is not bounded above. So what we have to prove is it diverges to infinity. So we have to prove that Sn diverges to infinity. We have defined earlier when we say a sequence diverges to infinity, if for given real number m, Sn is greater than m. So this for some n greater than or equal to m. So that we have to prove. So we shall write what we have to prove. We have to prove that given m greater than 0, there exists, or we have to find there exists n belongs to I such that Sn is greater than n greater than or equal to m. So this we have to prove. Then this shows that the sequence diverges to infinity. Now it is not bounded above. Sn is not bounded above, since so m is not an upper bound of Sn. Not bounded above means it does not have upper bounds. So m is also not upper bound. M is not an upper bound for Sn, or Sn means the range of the sequence S1, S2 and so on. So this means there is n. So therefore there exists n belongs to I such that some term of this sequence for this capital N, Sn, is greater than m. So there exists one term of the sequence S capital N which is greater than m, means m is not upper bound for the sequence. Now since the sequence is non-decreasing, the result one will follow. All the term of the sequence greater than this capital N will also be greater than m, because the terms of the sequences are increasing. since Sn is increasing or not decreasing, statement 1 follows because Sn is non-decreasing. Statement 1 is true and hence Sn diverges to infinity. What statement 1 is? Statement 1 shows that all the terms of the sequence are greater than m. So this particular term is greater than m, and then after the terms are increasing means that those terms are also greater than m, and that means the terms are increasing order and that are not bounded above, and therefore the sequence diverges to infinity. Hence Sn diverges to infinity. So this proves the result. Now, similar to these two results, when it is convergent and when it is divergent, we have proved. If it is bounded above, then it is convergent, and if it is not bounded above, non-decreasing sequence, not bounded above, then diverges to infinity. So, similar to this theorem, these two theorems, there is a theorem about non-increasing sequence, and we write that as theorem 6. A non-increasing sequence, a non-increasing sequence which is not bounded below, or which is bound, first we shall consider bounded below, which is bounded below is convergent. First part in the theorem, and two results we are listing in the same theorem, and second is a non-increasing sequence which is not bounded below. Diverges to minus infinity. Now, see this theorem 6, the first part is similar to theorem 4. A non-increasing sequence which is bounded below is convergent. For example, we may consider 1 by this sequence. This is a non-increasing sequence because the terms are 1 by 1, 1 by 2, etc. Decreasing actually. And but this sequence is bounded below because 0 is a lower bound of this sequence. All the terms are greater than 0, so therefore this is greater than 0 means 0 is lower boundary for this sequence, and this sequence is convergent, so it actually converges to 0. So that is the meaning of this result. And a non-increasing sequence again which is not bounded below, for that we may consider minus n sequence. Now what about this sequence? What are the terms of this sequence? Minus 1, minus 2, minus 3, etc. And you see the terms are non-increasing, actually decreasing. And this is not bounded below. There is no lower bound for this sequence. And therefore this sequence diverges to minus infinity. So that is the example for second part. Now the proof of the theorem is similar to the proof of theorem 4 and 5, and you should write the proof of this theorem. So what is the change? Bounded above is replaced by bounded below, and for proving the theorem related to the sequence which is non-decreasing and bounded above, we have considered the upper bound and least upper bound. So instead of upper bound and least upper bound, here we have to consider lower bound and greatest lower bound. So that is the change. So you should write similar, the proof is similar to theorem 4 and 5, and this is for homework. For homework view, see, proof is similar, not the same but similar to that of theorem 4 and 5. You refer, replace upper bound and LUB, least upper bound, by lower bound and greatest lower bound respectively. So you may consider, instead of capital M, you may consider M and take that as a lower bound or greatest lower bound for the sequence, and corresponding changes you have to do. So try for the proof of this theorem yourself. And further also there are some problems from the exercise 2.6. So I have written the solutions of these problems in separate, as a separate notes, and I will send you the problems to you. You should refer the solutions to these problems and try to understand. So this is about the two important results and the theorem as 4, 5 and 6. Now shall study operations on convergent sequences. Now, what are the operations on convergent sequences? Are simple, that is addition or sum, difference, product and quotient of convergent sequences. And we shall show that the sum, difference, multiplication and quotient also of two convergent sequences is convergent. Now these results are simple, and if you consider two sequences and operations of these two sequences, we consider the two sequences as Sm and Tn. The first result about this is that will be our next theorem. You may refer the number there. Is theorem 7. If Sm converges to L, or if limit n tends to infinity of Sm is equal to L, or inverse Sm converges to L and limit n tend to infinity of Tn, second sequence. Suppose this converges to L, T1, T2, etc. will be the terms of this sequence. Then the result is limit n tends to infinity of Sn plus Tn, this sequence. This will be a sequence, and the limit of this sequence is L plus L. So this is our first result. And next results we will be proving are like this. Limit, if Sn converges to L, limit n tends to infinity of C is a constant. C into Sn will be C times limit of Sn, that is C times L. And further result will be for difference. If limit of Sn minus Tn, that limit will be equal to L minus M. And next is limit n tends to infinity of Sn into Tn will be equal to L into M. And product, limit of product of the two sequences is equal to the product of their limits. And further, limit n tends to infinity of Sn divided by Tn will be equal to L upon M. Sn tends to L, Tn tends to M. So therefore, limit of Sn by Tn is L by M. Condition is M is not 0. So these are the operations on convergent sequences, and there are separate theorems about each result. So for plus there is result, and minus there is second theorem. For this scalar multiplication, C is a constant. Constant can be written outside the limit, C into L. So we shall consider the proofs are simple for these two results. Now you may refer the proofs. So only a few steps I will explain here for the proof of this. Now what we have to prove is the final result, the limit of Sn plus Tn is equal to L plus M. And by we have to apply the definition of limit of sequence. The definition of limit of sequence is important, and we are applying the same definition in these theorems. So when we shall say limit of Sn plus Tn is equal to L plus M, the absolute difference of these two is less than epsilon for n greater than or equal to capital N. And that means what we have to do is Sn plus Tn minus L plus M is less than epsilon for n greater than or equal to n. So this is the result we want to prove this theorem. And again we have given limit of Sn is equal to L. So apply the definition for this limit. So the difference of Sn minus L will be less than there exist. So I shall not write the proof in detail, but I will explain the important steps in this proof, and you may write the entire proof from the notes. So this is Sn minus L is less than, and instead of epsilon we will consider epsilon by 2. Epsilon can be taken at our choice. It is a positive number, epsilon is greater than 0, and this is true for n greater than or equal to n1. Instead of n we shall consider n1. So this result implies this one. And similarly, limit of Tn is equal to m, that will imply Tn minus m. Absolute difference of Tn minus m is less than epsilon by 2. Why we are considering instead of epsilon as epsilon by 2, that will be clear in further steps. N greater than or equal to n. Now next what we shall consider is both will be true for a maximum value of n1 and n. Suppose this n1 is 10, n is greater than or equal to 10 here, n1, and here say suppose n2 is say 20. Now both these results will be true for maximum value. That means if you consider n is greater than or equal to 20, then that is obviously greater than or equal to 10. So therefore both the results holds for maximum value, and that's why we shall consider capital N as maximum of n1 and n2. So let capital N is equal to maximum of n1 and n2. So then both the results holds, 1 and 2 holds. Then for this n, what we have is we shall consider mod of Sn plus Tn. This we shall consider Sn plus Tn minus L plus M. And now you see this is equal to mod of Sn minus L. We separate this plus Tn minus M, and both are equal. Now if you separate the absolute, that means the terms in absolute sign, the relation will be less than or equal to mod of Sn minus L plus mod of Tn minus M. So this is the property of absolute value function. Mod of a plus b is less than or equal to mod a plus mod b. And now if you consider, see, for n belongs to I, or for n greater than or equal to this capital N. Capital N is maximum of n1 and n2, and for capital N both the results are true. That means mod of Sn minus L is less than epsilon by 2. So this is strictly less than epsilon by 2. And similarly, mod of Tn minus M is less than epsilon by 2. So this is also less than epsilon by 2. And that gives epsilon. Epsilon by 2 plus epsilon by 2 is epsilon. And this happens for n greater than or equal to n. Not n1 or n2, but n, which is maximum of n1 and n2. And thus, finally, we have this is less than epsilon. So, which is what we wanted to prove. And this proves that limit of Sn plus Tn is equal to L plus M. Hence, the result. So, therefore, this shows limit. This shows this result. And thus, so this only the terms steps we have used are according to this final result. So that's why we have considered epsilon by 2 and epsilon by 2, because we are going to add this, and final result in final expression we want epsilon. So therefore instead of epsilon here we have considered epsilon by 2. This is at our choice. So whatever it may consider, epsilon is any positive integer, and thus the result is shown like this. Now the second result is of the theorem, next theorem 8. Suppose limit of Sn is L and C is a real number, and that means any constant. C is real number means constant. Then limit n tends to infinity of C into Sn is equal to C into limit of Sn, and that is 0. So this is our next result. Now this result is also easy to prove, and I will write here only the steps which are important in this proof. So here also, as like in the earlier theorem, so what we have to do is limit of Csn is equal to Cl, and that means final result we require is absolute difference of these two. Mod of Csn minus Cl is less than epsilon for n greater than or equal to n, by definition of limit of sequence. And if you prove this, we say limit of Csn is equal to Cl. And to prove this, we have to use the given, that is limit of Sn is equal to L. And if you trace this in reverse steps, then this C is constant, and that constant can be written outside. So therefore this will be mod C mod of Sn minus L is less than epsilon, n greater than or equal to n. And further, if you want Sn minus L, then that can also be written as mod of Sn minus L is less than, divide by both sides by mod of C, it is a positive number. So therefore that is epsilon divided by mod C, n greater than or equal to n. And thus we can start with this, because it is given limit of Sn is equal to L, and therefore there exists epsilon divided by mod C, positive number, such that Sn minus L is less than epsilon by mod C for n greater than or equal to L. And that is limit n tends to infinity of Sn is equal to L. Therefore there exists this symbol for there exists, n belongs to I, such that absolute difference is less than epsilon divided by mod C. Why we have considered epsilon divided by mod C? Because we want the final result in this form, and C is a constant. Earlier theorem, this is for single sequence. Earlier theorem there was two sequences Sn and Tn, and we have considered instead of epsilon as epsilon by 2. Here we have considered epsilon divided by mod C, and then further if you go in this direction, then multiply both sides by mod C, we will get this step, and then we will get this. And this shows limit of Csn as n tends to infinity is equal to C, and this proves the theorem number 8. Now there is next theorem which is important, and that we shall consider.